Okay, today we'll be looking at exponential growth and decay. We won't spend that much time on this topic, but if I have a object, item, or concept that's following what's called uninhibited growth or decay, uninhibited growth or decay, the equation that follows is one that has continuous compounding. The equation is one that has this basic setup. A of t is equal to a0 e to the kt, where, working backwards, t is time, t is time in the given units, you must watch your units carefully in this section. Then you have a0, which is the initial amount. Or the amount that you're starting with, or your starting balance, or starting weight. Another way of saying that is the amount at time 0. So you can always find it by plugging in 0. K is the rate of growth as a decimal. What is wrong with me today? And the rule for K is that if K is greater than 0, then you have exponential growth. And if K is less than 0, you have exponential decay. Let's look at a few examples where we kind of go through those properties piece by piece. Okay, as the size of a population of flies, yes, you heard me right, flies at time t in days. Notice right here that I am telling you that whenever I mention time, you have to use days. So if you're giving in hours, you gotta convert those hours to days. Is given by, and so that's going to be the amount of flies at time t is 300 e to the 0.05 t. Right, so they give us some basic information, and then they're going to start asking us some questions about it. But before we start doing that right here, let's just go ahead and explore the equation. The first number you see is 300. That's your A0. 300 initial flies. Some poor soul had to go through and count how many flies are in there before we start the experiment, and it's 300. Now you have an E right here. This tells us that we have exponential growth or decay. And what we have right here is what we call an uninhibited growth. Basically, the flies have as much of everything they need, and so they'll grow as fast as they possibly can. Under that situation, E is the base that we use. And then we have our R. Our rate is 5%. Notice that they didn't give it as 5%. They used the 0.05. They give the decimal that's equivalent to 5%. Remember, 5% is 5 over 100, which is equal to 0.05. Right? And then the last right here, the time, Remember, the time is our free variable. We plug in time to figure out how many, we plug in time, a number for time, and that'll tell us how many flights are there at that time. And so our time is in days. It's a free variable, right? So question, find the initial amount of flies. Question number 1. Find the initial amount of flies. Well, that's easy. Simply A0 is equals to 300. So the initial amount of flies is 300. If I wanted to work this out, I could plug in time of 0. Initial means time of 0. And that's going to be 300 e to the 0.05 multiplied by 0, which is 300 times e to the 0 power, because when I multiply the top, any number to the 0 power is 1, which gives me an initial of 300, but again, we already knew this. We didn't have to work that out. Number 2, what's the growth rate? The growth rate is simply 5%. And it's positive, so that tells us we have exponential growth as opposed to exponential decay. How many flies will we have after 12 days? What's the pop? After 12 days, and that simply means you have to find the amount when the number of days is 12. That's 300 e to the 0.05 multiplied by 12. And this is the answer if you don't have a calculator. But since you're doing this at home, might as well break out your calculator. When you work it out, you should get the answer of approximately 547. I have rounded to the first, to the nearest whole fly. And so about 547 flies. Just gotta plug it in, work it out. Make sure you can do it in your calculator without any help. Question number 4, which is a harder problem. When will the population be 800 flies? F-L-I-E-S. Oh my goodness. Well, the good news is we know it's going to be more than 12 days because the population is going to be higher than 547, right? And so we know that it's going to be higher than 800. But how much higher? Uh-oh. But how much higher? I'm gonna cut this part out. But how much higher? And so we gotta go ahead and solve. And so what we do right here is we set the equation equal to 800 because that's the number of flies we want. 300 e to the 0.05t. Again, question is when, so t is going to be my free variable that I need to find. So I gotta get to the t, so first I'll divide by 300. Again, I don't have a calculator, but I know the zeros cancel out. So that's 8 over 3 is equal to e to the 0.05t. Now I cannot make the bases the same, so to cancel the e, I take ln on both sides. The ln and the e will cancel out, and so that leaves me ln of 8/3 is equal to 0.05t, and of course that tells me I can divide the two to find t. When I plug that into my calculator, Again, T is about 19.6 days. And that's approximate. Just like that. The last question is, how long will it take the population to double? How long will it take to double? And there's a nice formula for this. It's called the double timing. The double timing is given by ln of 2 divided by the growth rate. That'll tell you how long it takes to double. And so that's equals to ln of 2 divided by 0.05. And so 13.9. That's going to be 13.9 days. So every 13.9 days, the population of flies will double. Which, when you think about it, that's crazy. There is a second way to work it out, but it's much longer. But I'll show you anyway. Since I'm trying to double the number of flies, if my initial amount is 300, then I will have 600 at the end because I'm trying to double my 300. So I divide by 300. Well, 600 divided by 300 is 2. And then I take ln of both sides. Ln of 2 equals ln of e to 0.05t. So ln of 2 equals 0.05t. So t is equals to ln of 2 divided by ln of 2 divided by 0.05, which is exactly what we did by using the double timing formula. ln of 2. So instead of doing all of that, you just need to remember ln 2 divided by k. That's how long it takes for us to double our population. If it was triple timing, how long will it take to triple? It'll simply be ln of 3 divided by k. Quadruple timing and so forth and so on. There's actually a half timing, which is normally called a half-life, and then this is just going to be a half. But we'll get to an example in a little bit. Let's look at one example of exponential decay. Carbon 12 is unstable and decays by the function. The amount of carbon that you have is equal to the amount of carbon you started with, e to the negative 0.00340. Now, this is not the actual equation, but hey, you know, we get to mix stuff up. Where t is the time in years. Okay. So, and we will start with 500 grams of carbon 14. It's carbon 14, not 12. 12 is the stable one. 14 is the unstable one. I'll go C14 right here. So, what is the decay rate? Question number 1. Well, the decay rate is simply K as a percentage, so I'm going to move the decimal point twice, so it's going to be 0.34%. Oh, because remember, this right here is your decay rate because it's a negative number. If I move the decimal point twice, 1, 2, I end up with 0.34%. And so that means every year I lose about 0.34%, less than a percent of carbon 14 every year. So it's decaying, but not at a very, very fast rate. Again, move the decimal point twice right here. So how much is left how much C14 is left after 50 years. Now the key thing right here is because this is negative, we will be losing carbon. It's not a growth, it's a decay. And so that's why they say how much is going to be left after 50 years. And so you find the amount of carbon after 50 years. Now the initial amount you started is 500, and then that's e to the negative 0.0034 multiplied by 50. Oh, no t. It's like my 10th mistake today. 34 multiplied by 50. And of course, that just goes into your handy dandy calculator. It's going to be approximately 422 grams. Rounded to the nearest whole number. That's simple. Just plug it in. On the other hand, when will only 200 grams be left? So if we start at 500, it's going to take us a while to get down to 200, right? But we know that 200 is the amount we're looking for. We start at 500, and then that's e to the negative 0.0, the k. But the t is the unknown. It says when. Just like previous. When they say when, they're looking for the t variable. So you leave the t variable free. And then you gotta solve for it. Steps are the same. Divide by 500. So you have 2 over 5. The zeros cancel. E to the negative 0.0034 t. And of course, get rid of the e, I take ln. E's cancel out. Ln and e cancel out. And so I'm left with the basic equation. Ln of 2 is equal to negative 0.0034 t. And of course, I can then divide by everything except t. Negative 0.0034, negative 0, that's 25, sorry. 0.0034. You work that out in your handy dandy calculator, and it'll tell you we need about 269 years to get rid of half. Get our carbon 14 down to 200 grams from our original amount of 500. The last question, D, is what is the half-life? Of carbon 14 in our example. Well, the half-life is the time it takes to get to half of the original amount. Time to half of the original amount. It's kind of like the double timing in reverse. The double timing was the time to get double the original amount. Your half-life is the time to get to half the original amount. But the formula looks pretty much the same. T equals ln of 1/2 divided by k. So in this case right here, that's ln of 1/2 divided by negative 0.0034. And so that's going to be approximately 204 days. You can solve the problem directly by setting equal to, if I start out with 500, half of that amount is 250, and solve, but it will end up becoming this equation, just like with the double time. Alright, and that's it. Good luck.